Sir, hello.
Now, are you able to hear me?
Sir, now we are able to.
Hello,
Sir,
are you able to hear me?
yes, sir.
Yes, sir.
Hello,
Yes, sir.
okay. Okay, so till now we have discussed the properties of the discretization. Now let us look at the nature of the discretization. Nature of So as an example, we'll consider a wave equation only. So this wave equation where A is positive. Now we want to discretize this at I and at N. Okay, so everything we want to discretize at ith space and nth or mth, you know, time. This time derivatives at nth and ith location and del u del x maybe at m, which may be n, where m is equals to n or n plus 1. Okay. N means present value or known value. It's better to write known value. And n plus 1 is unknown value. Now, how do we discretize this thing? So we know now that I can use forward difference. Okay, so I can say that I want to take forward in time and central in space. It is our choice. Okay, so we know that centrals in space is not a good method for this wave equation. But let us consider now, just to illustrate this example. So we have evaluated this at I and N, which is a forward difference at N. And here we wish to do this U I plus 1 central in space, U I minus 1 divided by twice delta x at any m. Okay, so now if if m is equals to n, then ui n plus 1 minus ui n delta t plus a is a constant, so we'll just keep it outside. A delta x in bracket ui plus 1 minus ui minus 1, and I'm writing n equals to 0. Now I want to express in terms of unknown and known. So unknown I'll put here and knowns I'll put in the right hand side, and I can write this as n plus 1 is equals to ui n plus a delta t delta x u I plus 1 minus u I minus 1 minus this is minus. Okay, you can write like this. So here you will see that everything is in terms of
Sir,
this unknown. Unknown, there is only one unknown. Okay,
sir, shouldn't it be 2 delta x?
there is only one unknown, and there are many knowns. Okay, so these are knowns, known values. This is a known value. This is a known value, and this is also a known value. There is only one unknown. So here there is only one unknown. Okay. And what this discretization is in terms of our x and timeline. So if I am talking about, suppose this is n plus 1 and this is n, and we have same grids size with uniform distances at I plus 1, I minus 1. So here what do you see? uin plus 1, uin plus 1, uin plus 1, this value is expressed in terms of uin, this value minus ui plus 1 n, ui plus 1 n value, this value plus this value, I minus 1 value. Okay, so this node values are only used in this expression. So n plus 1 node value and n node values at I plus 1 and I minus 1. This is called as a stencil. This is a stencil. This is called a stencil. And this stencil is a particular stencil of this stencil of forward in time and central in space. Okay. So backward method will have a stencil of this nature. They will have a 2 points and this kind of. Forward method will have the other stencil like that. Okay. So this is called as a stencil, which is used here. So you see that there is only one unknown and all these LOs are known. Okay. There is only one unknown and all are known. So to find, we can write to find ui at n plus 1, that is ui n plus 1, which is an unknown value, unknown. We use previous time level, that is nth level, and previous time level known values of ui, that is ui n, ui minus 1 n, ui plus 1. Such a formulation is called as, explicit method. Explicit formulation or such a method is called as explicit method. Explicit formulation. Okay. Also, we have noted that since space level values, all the space level values, I plus 1, I, space level, I plus 1, I minus 1, okay, etc. Space level values are at nth level, that is known level. The discretization this is discretization of del t is forward in time, which is called as forward in time. Forward in time. Forward in time. In short, it is called as FT. That is what we are in FT, forward in time. So here again you can note there is only one unknown and all others are known. All others are known. Okay. This is a explicit. Okay. Now, and the central in space, that is central in space. That there is no discrepancy. Okay. Central in space at nth level. So that is no discrepancy. Now, these problems, we have seen that there is a certain condition. So such formulations has to satisfy, have to satisfy certain condition on delta t and delta x for the stability of the solution. And we know that if the solution is not stable, then we may not get convergence. So stability is a important criteria, most important criteria to get a converged solution, to get the solution. Okay. Stability of the solution. So we have to satisfy this condition. Delta t, delta x should be. So for example, we have seen that. For example, Courant number, COURANT, Courant number, which is nothing but this combination of velocity delta t and delta x should be less than equal to 1. That is one claim. Now there is another number, that is Fourier number, or there are variety of names are available to them. Alpha, delta t, delta x square should be less than equal to half. Okay, this is for 1D. This is also for 1D. And if you have both the terms, like we got this a delta x, delta t, delta x as a coefficient of this del u by del x terms, and alpha delta t delta x square were the coefficients of diffusion term, and these are convection term. Now, among these two, whichever it will be small, that we will have to satisfy. Both the conditions then should be satisfied. Okay, both the conditions should be satisfied. Sometimes it may happen that your delta x's may be different. Sometimes this delta x may be different, then this delta x may be different. Here you may have different delta x, here you may have different delta x. So any delta x if you take from this grid, any delta x if you take, that delta x should satisfy this condition. And also any delta t you take in a time direction, this combination delta t and delta x combinations should satisfy this constraint. Okay. So there is a condition on delta t and delta x for the stability of the solution that can be chosen by the users. So you have to be very careful if you are solving this problem. But now this problem, if you see, this is like plug the values of uin, ui plus n, ui minus 1n, and get the value of left hand side. Okay. So here there is a simple substitution of known values to get the unknown values. Isn't it? Okay. So we need to just do it like y is equals to mx, like that. You know the m, you know the x, and just get the y. And keep on getting this y for different l. So at t is equals to 0, at t is equals to 1, t is equals to 2, you will keep on getting. Find these values. At I, if these are known, you find n plus 1, n plus 2, n plus 3, n plus 4, like that you keep on finding. Now, suppose if this, instead of this, if m is equals to n plus 1, if m is equals to n plus 1, if m is equals to n plus 1, then u ui n plus 1 minus ui n delta t plus a ui plus 1 minus ui minus 1 n plus 1 divided by delta x is equals to 0. Now here you see, here what do you see? Here what do you see? If you express this in terms of unknowns and knowns, now unknown is equals to known. If you do this, then how I can write this? A delta t delta x. I think I have missed here also, isn't it? So this I'll write ui minus 1 n plus 1 uh, plus a delta t twice delta x u let me write with I first, because I minus 1, I and u I plus 1, that will be better. There is no, I mean, this is not compulsory, but I'm just writing it. I n plus 1 and plus a delta t twice delta x u I plus 1 n plus 1, isn't it? And then is equals to this term we are taking out, so ui n. Okay, so what do we see? We see that the known is this and unknowns are this. Okay, so what do you see? There are here more unknowns, more than 2. Okay, more than 2, 2 or more than 2. Here 2 or more than 2, 2 or more than 2, 2 unknowns are present, and okay, so there is no need of very few or this thing. Ui can be more than ni1, ni plus 1. Okay, that is also possible. And known values, not leave it this thing. Only condition is that unknown should be 2 or more than 2. Okay, so that we can see. And enough, and we can, if I do it right, then I can write in another word, and enough known values. If anything is not there, at least it will be 0, isn't it? Okay. So this thing is there. Now, suppose I want to see the stencil of that, of this scheme. Now, what do you see? Suppose this is X, this is T, and this is N minus 1. Suppose this is N and this is N plus 1. Okay. So we are moving in time and all our eyes will be set. This is 1D problem. So your eyes will be here only. Grid points will not change with time. So let these grid points are there. And we say in a general way that, so what do you see? UIN plus 1. UIN plus 1 is this. Okay. This is there. UIN plus 1 is there. Isn't it? UIN plus 1 is there. Then UI minus 1. UI minus 1 N plus 1 is there. UI plus 1 N plus 1 is there at N plus 1 time. Okay. And UI and there is a nth term. So nth term is this one, blue, yellow. Okay. This one. Now, what do you see here? Our stencil now become reverse. Isn't it? Previously, it was, this one was N plus 1 and all other were N level. Now, the thing is now different. Okay. Okay. So this is a stencil for this particular. This is also FTCS. No, this is not FTC. Why? We'll see. This is called as backward in time, BTCS. We'll see now. Why we call backward in time. So as you wrote for forward in time, we'll also say that why we are saying, because all our discretization at space level, they are at N plus 1th level, and hence it is called as backward in time. All our calculations we are doing it backward in time. We are trying to calculate for the present time and then we are picking the value. Here we were trying to calculate the future value with present values. Okay. So this is a stencil to make it a comparative stencil of BTCS, backward in time, central in space. This is, which is nothing but this scheme, which we have shown here. Okay, now so again we will note here to find UI at UI to find UI, comma UI minus 1, comma UI plus 1, etc. at N plus 1. Okay. we have more than two unknowns, we have more than two unknowns. Such formulations are called as implicit. Implicit formulation. Okay. So what does it mean implicit? It means that not known before. Not known before. And explicit means they are already known before. Okay. Now about that VT, since space level values, values are at n+1 the time level, the discretization of this discretization of del t is backward in time. Backward in time. PT. And the special derivatives are central in space. So central in space. So that is the reason we are saying that is the BTCs. And what was the third point we mentioned here? These problems, such formulations does not have the restriction of delta t and delta x, as these methods are unconditionally stable. Okay, so there is no condition needed in order to use this particular method. There is no condition, so there is no restriction on delta t and delta x as such. Okay, but we know just to make a note, but we know that from our but we know that using larger delta t and delta x, like that. Delta x means any x, y, z also, and delta x. The truncation error increases. Therefore, even there is no stability, therefore it is wise. Therefore, it will be a wise decision to consider reasonable delta t delta x values. Reasonable delta t delta x values. Okay. Next, what was the classification? So there is no Fourier number criteria, and here there is no simple substitution. So as you see, as you can observe from the equation, as you can see, there is no direct substitution. There is no direct substitution of known value to get unknown value. Okay. This is because we have more unknown. This is because we have unknowns at I plus 1 and I minus 1. Okay, etc. So there is no direct substitution. So what do we do in this case? So we need to calculate I plus 1, I minus 1 simultaneously. So we need to calculate, we need to calculate ui n plus 1, ui minus 1 n plus 1, ui plus 1 n plus 1, etc. simultaneously. What do you mean by simultaneously? So if you see this equation, that equation was looking like I minus 1 n plus 1, isn't it? And that was some beta plus ui n plus 1 and plus beta u I plus 1 n plus 1, and it was ui n. Now if you see this particular left side, we can express in this form. Isn't it? So we can write in this form. Other terms will also be there in a matrix form. in a matrix form, we can represent all these terms here. So here we have to solve a matrix system of this nature. Ax is equals to b. Okay. So we need methods of solution, methods of solving simultaneous equations. Okay. So, and in one case, you need to be very careful about delta t delta x. In second case, you need not to worry about delta t delta x. But in first case, you need not to solve this matrix simultaneous equation. But in second case, you need to solve simultaneous equation. Okay. So in one case, programming or calculation procedure will be very easy. Here, programming to solve this simultaneous equation may be little complicated, but you may not have restriction on delta t delta x. Here, there is restriction on delta t delta x, but the method of solution is very easy. Okay. And these easy methods, explicit methods, are very good for parallelization. Okay. Since there is no matrix, okay, so there is a simple substitution. Therefore, they are very good for, therefore, they are preferred. They are preferred in parallel programming. In parallel programming. Okay. And here these are little cumbersome. These are cumbersome to program parallelly and to use in a parallel program. To use in a parallel program. Okay. But this delta t and delta x, but delta t and delta x are usually not known. Usually not usually not known a priori. Is not known a priori in a general solver explicit methods are rarely used. I'm not saying that they are not used. They are there. You may see in many softwares they will be there. Okay, but they are least preferred because these delta t delta x may not be known. But their LES, large simulation problems, and these things, these methods are very good for doing large simulations type calculations. Because time taken to calculate will be small compared to this. Here you have to do iterative process. Okay. Conversion to parallel due to large iterations large iterations needed. So you might have to do various needed and handling of the matrix may not be straightforward. May not be straightforward. Straightforward. Okay, so these are most widely used. These are most widely used methods as we do not have restrictions on delta t, delta x. Also, these methods are good for non-linear problems, are good for solving non-linearity. Okay, so we have seen now, okay, you remember this, what is explicit, what is implicit. So now we'll see one more basic, that is how do we solve this method of solving simultaneous. So we'll now move on to our task. Next task is to study method of solving simultaneous equation. Excuse me. Okay, so most popularly used methods are categorized into two. There are two methods. Number one is called a direct method, where we solve directly the matrix, direct methods, and another category of methods is called as iterative methods. Iterative methods. Okay. So in this case, we directly solve solve the matrix to get solutions, and here we perform iterations starting with some Gauss value, Gauss value, and correcting with some Gauss value and correcting the Gauss values in the next iterations. Okay. Examples of this direct method is one popular example is Gauss elimination method. You heard of this, isn't it? Gauss elimination. Okay. Or a basic method which is also called as Crowd's method. These are some of the examples. Iterative methods, on the other hand, the popular methods are called as Jacobi method. We have Gauss-Seidel method, and we have other methods of variation of this Gauss-Seidel. Relaxation. Gauss-Seidel relaxation methods. Now we'll see one by one what are these methods. But before that, let us discuss about properties of these linear simultaneous equations. Properties of linear simultaneous equations. Okay. So let we have this system of equation a1x plus a2y is equals to b1 c1x plus c2y is equals to b2. Okay. Now, if you see how many unknowns are there? First question we asked, how many unknowns? Unknowns are, how many unknowns are there? X and Y. And how many equations? 2. Okay, equation number 1 and equation number 2. Equation number 1 and equation number 2. So this system is solvable. This system is solvable. Okay. Now, it means that solvables, we have an existence of solution. Existence of solution. Now, other question is that solution unique? We are interested in unique solution. Is that solution unique? Now, it depends upon the equation itself. Okay. The properties of this linear symmetry equations itself. So suppose we have these two lines. These are like equations of lines. So we may get either number 1 case for equation 1 and 2. 1 and 2. We may get following situations. Okay. Number one situation. If I plot this graph and observe that my x and y, now I observe that I get two equations of line in this fashion. So this is a equation 1, suppose, and this is say equation 2 line. Now they are intersecting at one point, and this point of intersection is called as a solution. Okay, so this is a solution. And there is no other place where there is an interaction or intersection. So here, if this is the case, then here we have a unique solution. Here we have a unique solution. Now, suppose we have other situation where we have a representation of this nature, x and y, where we get equation number 1 like the line from equation number 1 like this, and another line which is parallel to this, which is equation 2. Okay. Now in this case they do not intersect. So here, this case, we have a no solution. So here we have no solution. Okay. No solution. Here there is no solution. This is a singularity. This is called a singularity. Why this is called a singularity? Because what is happening over here is, suppose you extend this equation here, this is the intercept, and here this is the intercept. Equation number 1 is just a shift of equation number 2. Suppose you have x plus y is equals to 1, then it is just a shift of this x plus y is equals to 1, maybe by a certain number, say 2x plus 2y is equals to 2. These may be two equations, two variables, but the second equation is simply the combination of first equation. So the you already have done these things in case of matrix properties. So if this is the case where any equation can be expressed in terms of linear combination of any equation, then we may not get a solution. So this is a singularity. So there exists a singularity. This is called a singularity. It doesn't ensure that you are going to get the solution. Here they are not represented as a linear combination of any equation. So all rows and all columns are independent of each other. They are not expressed. All rows and columns of this matrix A, if you say now this is a matrix here, 1 1 2 2, they cannot be represented as a linear combination of any. So here it is a unique solution. Number 3 case can also be there. Maybe you have a intersection. If you have an intersection, maybe you can have an intersection, but that intersection itself on the same line. Okay. It may be exactly on the same line. That is also possible. That intersection may be on the same line. Okay. Now equation 1 and equation 2, they are representing the same line. So infinitely many solutions. Okay. This means that they are intersecting each other, but there are infinitely many solutions. This is also case when you have only you have linear combination by you have multiplied this first equation by 1. So simply second equation remains same. So infinitely many solutions. Okay, infinitely many solutions. This is also singularity, also called as singularity, and we do not want singularity. A matrix should be such a way that, so essentially we mean that this matrix should be such a way that we do not get any singularity. Okay. Now, there can be another situation. The next situation, fourth situation, if the situation is of this type, where you have two lines intersecting each other, okay. So this is equation 1 and this is equation 2. And now here is the solution. isn't it? This is our solution. This we will say a solution. Now, suppose by chance, suppose this equation by chance, suppose this equation is x plus y n is equals to 1, and now by chance this second equation is okay. Now say second equation is x plus 2y is equals to 1, for example. Now by chance this coefficient 1, now by chance this coefficient 1 becomes 0.99 x plus 1.99 y is equals to 0.999. Now, as an engineer, we know that 0.99 is very close to 1 and 1.99 is very close to 2. 0.99 is very close to 1. So we may say that these two equations are nearly same. But if you plot this equation here, the line that the equation of that line, I mean the line of that equation on the graph may be passing in this manner as shown in the figure here. So I'm drawing by green color the shift of this line. It is just a shift of that. Suppose it is shifted by just what is that? We are 1 minus 0.9. Okay, that is just a shift we have. So just small epsilon. Okay, we may say that rather than saying, we can say this as this is, say we can 1 minus epsilon. Okay, or the number or coefficient minus epsilon. So it is just shifting by that epsilon. It is just shifting by that epsilon. So I can write that shift by epsilon by drawing another line equation. I mean line from that equation, and it will be parallel to that, and it is parallel to the white line. Okay, and this is this equation 3, which is very close to equation 2. Equation 3, which is very equal to equation 2. But you see that here is a solution. Solution is here. This is our solution of equation 3, and this is our solution of equation 2. So by a small shift, which is very negligibly small, which is epsilon kind of shift, we get a change in the solution very abruptly. From x2 we got a very large value or very small value in this case, or in magnitude, in terms of magnitude, a small large differences in the values we can see. Okay, so for a small delta we can have a large change in the solution. So in this case here, what do we see is here for a small epsilon there is a large difference in the large change in the solution. Okay, so although these two equations looks very similar, but because of small epsilon, your solution may get change, and such a system is highly ill-conditioned. This system, if it happens by chance that if you make a small change in this representation of this, and you get large values in the solution. This is a unstable system. This will only happen when the system is unstable. This system, say for example, and this is suppose with some coefficient, a1, a2. This is, I am not saying that this x plus y is equal to 1, x plus 2y is equal to 1 is unconditional, unstable. Just to show you representatively, I take one example which may or may not be unstable. But assuming that this is an unstable case when there is a change in small x, small value of epsilon. So this is an unstable system, and also it is called an ill-conditioned system. Ill-conditioned systems. Okay, and since the system is unstable, it will not give you solution. Okay, it will not. The iterative method, the iterative or direct method will not be able to give you, solutions at all. Converse solutions. Okay, give solutions which are converse. Converse means stable. Stable means converse. Okay. So stable solution is always converse. Always converse solution is stable, but it may not be correct. That is also. Okay, so they do not lead to. So what do you mean by ill conditioning? So you got these properties. What properties this matrix should have? Matrix should be such a way that you get unique solution. Unique solution will be obtained when their rows and columns are such a way. So property of the matrix will be such a way that you get a unique solution. If it has any rows and columns which can be made combination of each other, then you get these singularities, infinitely many solutions or no solutions, or you may get a system of matrix where any small change due to round off error or rounding takes place in the computers may drastically change the solution. And if such a system is there, that system, no matter how you do, you are not able to get a stable solution. So the ill-conditioned system should not be tackled. Ill-conditioned systems first should be made conditioned. And how to do that is the question, and that we will see. Before going to that, what is ill-conditioned system? Well, what are ill-conditioned systems? What are ill-conditioned systems? Okay. The system whose matrix, say A, has a large condition number. Okay. Condition number. Large condition number, which is represented by kappa of matrix A. Okay. This means that condition number of matrix A. This we read as condition number of number of matrix A. Okay, we read this kappa A as a condition number of matrix A. And matrix A is nothing but coefficient matrix. Okay. Matrix A is a coefficient matrix of linear simultaneous equations. Linear simultaneous set of equations. Okay, and how it is defined? The condition number is condition number of matrix, say A, kappa A is equals to a matrix norm of matrix A multiplied by the matrix norm of A inverse. So first thing first, for condition number to check, any matrix should have an inverse. And you can take a max norm of that matrix and A matrix and max norm of A inverse matrix and multiply them. And if this kappa, is very large, okay, very large, okay, then the system of equation, or matrix A is ill conditioned. Okay, an ill-conditioned matrix will not give you by any way a solution, converse solution. It will create difficulty in getting convergence. The value of K, the range of K is from 1 kappa A to infinity. Okay, the range of kappa A is generally from 1 to so ill conditioning need to be removed, and that depends upon the matrix A and max norm. And essentially, max norm is dependent upon the coefficients of the matrix. Coefficients is the values of the matrix. Okay, rows and column entries. Okay. Now we'll move on to the Gauss direct method, one direct method, that is Gauss elimination method. So in Gauss elimination method, let we have these equations a1 x plus excuse me, a11, a12, x1, x2, a1n, xn is equals to 0, or a21, x1 plus a22, x2 plus a2m, xm is equals to 0, and we can generalize it to n1 x1 plus a n2 x2 plus a nm xn equals to 0. We can have this general system, and we can write them as a11, a12, a1m, a21, a22, a2m, an1, an2, and anm. Okay, and this is n is equals to m system. You can write like this in a matrix form: x1, x2, x m on the right hand side. Okay, so in Gauss elimination, what do we do is we convert into this, we make all these entries below diagonal entries 0. Okay, so we make these entries entries 0 by algebraic manipulation or row column operations. Okay, so finally we convert this into a matrix of this nature: a11 prime, a12 prime, a1m prime, a22 prime, anm prime, x1, x2 up to xm is equals to this b1, b2, bn. This may not be 0, because after doing these operations, you may get some changes here. Now we solve this system. Now this system, this process, this is called as forward elimination. This is called as forward elimination. This is called as forward elimination. Okay. So we move forward and eliminate. We move forward and eliminate. First we eliminate, say, this one. Then we eliminate other two entries. Then we keep on eliminating the rest of the entries. Moving forward. Okay. So with moving forward, we make all other entries 0. And above entries, there should be values. This is called as forward elimination. Now, once you have done forward elimination, the next step is called as backward substitution. Backward substitution. Now, in the backward substitution process, you know that this A N M prime XM XM is equals to BM. So from this, we can get XM, which is nothing but equals to BM divided by ANM prime. So XM is obtained now. Next equation, just before this, there will be A n minus, n minus 1 M A n minus 1 M minus 1 and A n minus 1 M minus 2. So those second from second, this term is already gone to 0, so this term is not there. Only 2 are there. So from second equation, we can have A n minus 1 M minus 1 prime X M minus 1 plus A n minus 1 M prime Xn is equals to Bm minus 1. Okay. Since Xm is known, we can write A prime n minus 1 M minus 1 X M minus 1 is equals to Bm minus 1, okay, minus A n minus 1 M prime multiplied by Xm. So Xm is Bm divided by A prime Nm. And Xm minus 1, this will give you Xm minus 1, this particular term M minus 1, and this value A prime N minus 1 M Bm A prime Nm divided by A prime N minus 1 M minus 1. So X M minus 1 is obtained. Similarly, you can obtain X M minus 2. Then likewise, you keep on calculating, and finally you can calculate X1. Okay. So just by back substitution, because every time we will be knowing the previous values and only one unknown. So you keep on by back substitution, we get explicitly a solution. In the back substitution, we get explicitly a solution from the back side. From the last solution to first solution, you get a solution. From Xm to X1, you get a solution. Okay. As an example of Gauss elimination, you should practice these examples using calculators. Suppose you have a system twice x plus y plus z is equals to 1 and x plus 2y plus z, 2y plus z is equals to 1 and x plus 1 by 2y plus 2g is equals to 1. Now this system we can write like 2 1 1 1 1 2 1 1 sorry 1 half 2 and 1. Now you can eliminate, so row 2 twice row 2 minus row 1 will eliminate this element, isn't it? So and the twice of row 2 twice of row 3 minus row 1. Okay, so this operation will give you the values 2 1 1 1 and this is 0 and twice of this 4 minus 1, so that is 3 and 1 1 2 1 2 1 and this one twice, this becomes 0, this becomes 0 and 2 of this and this is again 3 and 2 of this minus 1 1. So we see now that x3 thrice x3 is equals to 1. This gives us x3 is equals to 1 by 3 and second equation we have thrice x2 plus x3 is equals to 1. So this equation thrice x2 is equals to 1 minus 1 by 3 gives x2 is equals to 2 by 9, isn't it? And you just find it out. Okay. Then third equation, from third equation, equation number 3, twice of x1 plus x2 plus x3 is equals to 1. This will be twice of x1 is equals to 1 minus 1 by 3 minus 2 by 9 and this gives x1 is equals to again 2 by 9 and you can cross check by substituting. So this is a solution. This is a forward elimination and this is a back substitution process. This process is a forward elimination. And this process is a backward substitution. Okay. Now you have one method. So shall we use this method for always? Okay. No, there is no possibility. Why? The reason is now the number of operations here, the number of operations which are performed here, the number of operations performed here during forward elimination and backward substitution, the number of operations are such that if this matrix is very high, Now this is only 3 by 3. This is a 3 by 3 matrix. Suppose you have very large matrix. Okay. So these methods have a problem. Okay. For disadvantages, the method has a disadvantages. Okay. So for large matrix, and these large matrix or matrices, which are usually occur in most of the engineering application, most of the engineering applications or any mathematical applications. The Gauss elimination method gives large round of error producing erroneous results. Okay. So accuracy is not good for higher system and they become cumbersome. Second problem with this is the pivoting. Okay. Pivoting is a problem. Pivoting is a problem. What is pivoting is? So while performing this operation, row operations, you may divide by this central coefficient. All these diagonal elements are called as central coefficients. Okay, why they are called as central coefficients? Because when I am talking about the x1, my term which is a coefficient of x1 is a11. When I am talking about x2, the coefficient of x2 is a22. Coefficient of xn is an. So that is the reason they are called central coefficients. So center of interest are a1, x1, x2, xn. Correspondingly, their coefficients are called as central coefficients, which are on a diagonal. So these values you may divide, you may do operations such a way that you may also need to divide here on other elements. Okay. This diagonal entries. Okay. Or in other word, if I have to say now in this operation, when we were converting, we are taking a row transformation, we were essentially multiplying the row and then subtracting from the row 1. If R1, this element is 0, for example, then we could not, subtract by 1 minus even that R1 wouldn't have given a solution. Only other option could have been that swapping of the rows. So that 0 comes here and this goes there. So the central coefficient should not be 0. Okay, in most of the cases, this thing should not be 0. Central coefficient should not be 0. That is a condition. So if pivoting element is 0 at some point of time and you are doing division or like this operations, then you may not get the solution and it may create a problem. Okay. So pivoting is a problem which you may find difficult to handle. Okay. So therefore, Gauss elimination method is rarely used. Method is rarely used for general CFD solver. Okay, CFD solvers are meant to solve large, practical problems which having a large, this coefficient matrix. So these methods may not be so useful in this case. So most of the time, Gauss elimination methods are not used. And to get around this, iterative methods are preferred. Why they are preferred, we'll see once we. Iterative methods are preferred. Okay. Then what are those iterative methods? Let us see those iterative methods. As we said, iterative methods are like Jacobi, method. Okay. What is this method is? So we again consider that A11 x1 plus A2 A12 x2 plus A1m xn equals to P1 A21 x1 plus A22 x2 plus A2m xn B2, and likewise you can get Bm plus Anm xn plus An2 xn An1 xn. Okay. These equations are written in this form. So first equation is written like x1 is equals to P1 minus A12 x2 minus all other terms minus A1m xn divided by A11. From second equation, we write x2 is equals to then 1 upon A22 B2 minus A21 x1 minus A23 x3 minus likewise minus A2m xm. Similarly, writing for xm is equals to A 1 by A n m B m minus A n 1 x1 minus A n A n m xn like this. Okay, you can write like this. So here these are the Gauss values. These are the Gauss values. What are the Gauss values here? The Gauss values are x2, x3, x4 up to xn. These are Gauss values. Gauss values in the beginning. Okay, Gauss values at ith iteration, first iteration, zero iteration or first iteration. First iteration. Okay. And then all others are like that. These are Gauss values. These are also all these values. Okay. So it is just an expression in the form of, okay, in the form of these known values. Whatever the simultaneous equation was there, what we did is that all these are n minus 1 terms. Okay, all these are n plus 1 terms, n plus 1 terms, n plus 1 terms. But what he said that these n plus 1 terms, we assume to be known, n. We assume them to be known, n, and this is only unknown. And from that Gauss known, we calculate unknown and we keep correcting this unknown. In that sense, it is iterative. Okay. So in Jacobi, we take x1 and x2, x3 like this, and again you calculate. Similar procedure you also follow in the method called as Gauss-Seidel method. Okay. Second method is also called as Gauss-Seidel method. Gauss-Seidel method. Now, in that method, you again get x1 is equals to 1 upon a11. Same thing, b1 minus, but then what is the difference? So that we would like to see that a1m, same. That is our objective, to see Jacobi over Gauss-Seidel method. 1 a22 b2 minus a21 x1 all minus, and then a2m xm, and xm is equals to a_nm bm minus a_n1 x1 minus up to minus a_nm xn. Now here, in both the cases, x2, x1, x3 up to xn, these values will be given. Say Gauss value. This is a Gauss value. Say it is a 0. Okay. So this value, 0 value, will be substituted here. 0 is substituted, 0 is substituted, so you got x1. Next time, in Jacobi method, x1, x2, x3, xm, they are all zeros. So x1 is made 0, x3 to substitute 0, and x2 is obtained. Similarly, x1 is 0, likewise xm is 0, xm is calculated. Okay. Then whatever these calculated values are there, so let me write 1, 1, 1. Now our x1 will be equals to x1. Now for the iteration number 2, iteration 2, second iteration, iteration 2, x1 will be x1, x1 1, and x2 will be equals to x2 1, x3 will be equals to x3 1. Likewise, xm will be equals to xm 1. Now with this x1 prime, and then you calculate another set which will be x1 2, which will be equals to 1 a11 b1 minus a12 x21 minus a1m xm1. Okay, x22 will be equal to 1 upon a22 b2 minus a21 x11 x11 still x11 minus a1m xm1. Likewise, you get xm2 is equals to 1 over a and m b m minus a n1 x11 up to a and m xm1. Okay. In the next iteration, number 3. In the iteration number 3, iteration 3, you have x1, x1 2, x11, sorry, x11, x21, x21 is nothing but equals to x11, sorry, x11 is equals to x12, and x21 is equals to x22, x3 1 is equals to x3 2. Likewise, you can, and then again you calculate x1 3, third iteration. 3 means third iteration is equals to 1 over a11 b1 minus a12, and this a22 like that, a1m xm2. Okay, 3. So previous iteration 2. So likewise you can do iteration. Now here what we are doing, here we are saying x1, x2, x3, xn are 0, same. So we substitute 0 here, we obtain x1. Okay. Now here this value is 0, but this x1 is this value, and all other values x2, here there will be x2, x3, there will be some a 2, 3, x3, this x3 will be 0. But x1 will be whatever x1 now we obtained here. Okay, so this value will be x1 value. So latest value of variables will be coming. This is a guess value. This is a guess. This is a guess. This is the guess. This is a guess. First time you have to use all the guess values. Then once we calculate a corrected value, that corrected value is substituted along with all other values. They are not corrected values are available. So guess values only are used. Now in this equation, next equation, x2 is known and x1 is also known. So except x1 and x2, all other values for x3 calculation, x1 and x2 will be used and all other will be guess values. Similarly for m, all other values before xm means m minus 1, and all this like. All values less than m, these will be obtained from this iteration. So xm value will be using all the values x1, x2 up to x3 coming from, so n minus 1 should be there, and n minus 1 here, n minus 1, because we are talking about this last term. So m minus 1, k xm minus 1 should be here. Here also we are talking about last, so m minus 1, m minus 1. So here also in the last it should be minus 1, m minus 1. Okay, you correct this, m minus 1, m minus 1. Here also m minus 1, m minus 1. Okay, so we choose the latest value. So now in the next iteration, next also in the next iteration, iteration number 2, our guess values x1 will become this, x1 1, x2 1, x3 1, and x1 1, x2 will become x2 1, and x3 will become x3 1, like that. And again we calculate x1 second iteration value, x1 1 over a11 using, since we x1 at second iteration all other values are these values, so we'll use these values. These values are used here. Now x2 2, x2 to 1 a11, this x1 value will be used here and rest other values will be used. For x3 2 a33, we will use these values, x1 value, x2 value, and this x3 value, and likewise other values. Are you getting this? Okay. So what do you mean? What do you see difference in this? In the first iteration, all the guess values are used here. All these are guess values. All these are guess values. Guess values, guess values, guess values. But here, first time we use guess values. Here, first time we use guess values. Then we use the latest value. This is the latest value. And then these are guess values. Then again, we take two latest value, rest of the guess values. Here, all are latest value. These are all in the last equation. We will have all latest values. Okay. You got this? Have you got this? So we can see this by an example. We can see this by an example. So let me take very simple system. Twice x1 plus x2 is equals to 1 and 3x1 plus 8x2 is equals to 1 itself. Okay. Now this method and initial guess is x1 is equals to x2 is equals to 0, say. Okay. So this is a guess. Now Gauss method, Jordan method. Sorry, Jacobi method. Okay. Now in the Jacobi method, x1 is equals to, first we will write this first equation in terms of x1, 1 minus x2, okay, divided by 2. And x2 will write from the second equation 1 minus thrice x1 divided by 8. Okay. Now according to this case, so iteration 1 will give us x1. x1 is equals to 1 minus, what is x2? x2 is 0. 1 minus 0 divided by 2 is equals to 1 by 2. And x2 is equals to 1 minus 3 into 0. x1 is 0. x1 is also 0. So 3 into 0 by 8 is 1 by 8. Now iteration 2. In the second iteration, x1, now I'll write like one iteration. Second iteration. Now here iteration is looking like a known and unknown, okay, isn't it? So here 1 means unknown and x1 0 means known. Guess values will be x1 0, x2 0, x3 0, like that you can write. So x1 1 is equals to, like that, x1 2 will be equals to 1 minus x2 1 divided by 2 and x2 2 will be equals to 1 minus 3 of x1 1 of 8. Okay. What are these values? 1 minus x21. x21 is 1 by 8 divided by 2, and you will have to get 7, 16, and this is 1 minus 3x11, so 1 minus 3 by 2 over 8, so 2 minus 3 minus 1 by 16. Okay, so likewise you can keep on calculating the values of x1 and x2. Okay, and when to stop? When we find that difference between the previous iteration. So like if difference between these x1 and n plus 1 iteration minus x1 n iteration, this magnitude less than some number which is very small number, which is equals to 0. So equals to 0 means 10 to the power of minus 5 or minus 6. Okay. Right. Similarly, x2 also, second variable. Add next iteration minus previous iteration. x2 at previous iteration should be less than epsilon. This epsilon for all variables can be same. Epsilon is a is a very small number. Very small number. Okay. This is about jackpot with 2 iterations. Now, in case of Gauss-Seidel method, x1 0 is already given as 0. Let me just write that x2 0 is 0. These are guess values. Initial guess is given. Initial guess is given like this. So iteration 1 will give you x11 is equals to 1 minus x20 divided by 2, which will be equals to 1 minus x20 is 0, 1 minus 0 divided by 2 is equals to 1 by 2, and x21 first iteration value 1 minus 3 of x10 divided by 8, 1 minus 0 divided by 8, again 1 by 8. Oh, what happened? At first iteration, we got the same values. So, we do not see that much difference in the first iteration. So, let us go to iteration 3, the second. Iteration second, x1, 2 will be equals to 1 minus x2, 1 divided by 2, which will be equals to 1 minus 1 by 2, 1 by 8 by 2. Again, it is looking like 716. Then, is it correct?
Hello, sir. Sir,
Yeah, it is not correct. Why this looking same? Because here is a problem. Here we should have taken x1, 1, latest value. Okay. In this case, x2 is not known. To calculate x1, x2 is not known. But to calculate x2, x11 is calculated. So x11 is 1 by 2. So this is 1 by 16. So x2 2 is x2 1, and that is 1 by 16. So you get changes in the 15 by 16. Okay. And x2 2 is equals to 1 minus 3 times x1 of this 2, this one. So I again make it point here that we are using this value, latest value. This is used here. This value is used here. And here, these values are coming from the previous one. New guess value. These are new guess value. This is latest guess value. 8, 1 minus 3 into 15 divided by 32, 8, and you can get this. Okay. So 32 minus 32 into 8. So we see that we are, getting different results, and then we again cross check by using this whether we got conversion, and then that iteration moment we stop. So if this difference of this is very small, then we stop. Okay. And now what we find that suppose we do Jacobi method and suppose we do Gauss-Seidel method. Since Jacobi is using Gauss values in a particular iteration one time and no use of latest values, Jacobi method is if it is taking n number of steps or n number of operations, the Gauss-Seidel method takes n by 2 operations. Okay, so this is quite fast, faster than twice faster than Gauss-Seidel method is. As in the Jacobi method, latest values are not used, latest Gauss values or values are not used. You cannot say all the time Gauss values, latest values are not used, values are not used. It is slow as compared to the Gauss-Seidel method. Gauss-Seidel. Okay. And if n operations are taken by Jacobi, the Gauss-Seidel, GS, sometimes it is right, GS, the GS will take n by 2 operations to solve the same problem. Operations to solve the same problem. Okay. Therefore, Gauss-Seidel method, GS method, is most widely used in general CFD solvers. Okay. Okay. So this is, now we said about Gauss elimination, then we said about Jordan, and then we are talking about Gauss-Seidel method. Okay. So Gauss-Seidel is now, we got to know that Gauss-Seidel method is the one which we will be preferring for our problem solutions. Now, when we have this system of equations, we have this A and X and B. Now, when you have this system, the question is, will the solution procedure converge. Okay. Solution procedure, iterative procedure. Iterative, will the iterative solution procedure converge will converge to or lead to solution converge. Okay, or will the iterative procedure will produce any solution? That is the question. And in what condition? Is there any condition? Is there any condition that leads to that ensures convergence? Okay, that ensures convergence. Is there anything like that? So that is very important step in this process. Okay. So that is called as a criteria, which is named as Scarborough Criteria. Scarborough Criteria. Now, what is this criteria is? What happened? Now, suppose we have this matrix 2, 1, 1, 1, 2, 1, 2, 1, or 1, 2, 3, x1, x2, x3 is equals to b1, b2, b3. Now, according to this criteria, what it says that in every row, the central element, now central element in this first row is this. This should be greater than or equal to sum of other elements. Other elements are this. So 1 plus 1. So this is satisfied. Next, second. In second case, 2 is again there and others are 1 and 1. So 2 is greater than equals to 1 plus 1. Satisfied. Okay. And in other case, last equation, this is also there. 3 greater than or equals to, they are all equals to 1 plus 2. This is also satisfied. If this is satisfied, then it shows that there is a diagonal dominance. Okay, there is a diagonal dominance. This diagonal term should be larger than the or equal to the sum of the rest elements. That is a condition. The diagonal element should be larger or equal to this. Okay. It can be larger at in all. That is a very good situation. Greater than situation is very good in all. If not, now in this case, this condition is not satisfied. What is this condition? This equal to condition is satisfied. Equal to condition is satisfied. Here also equal to condition is satisfied. Here also equal to condition is satisfied. But at least in one row for convergence, at least one row in a one row, at least in a one row, the central element AII should be greater than sum of other elements. Okay, so I where I is not, I mean JJ you can say, where J is not equals to I. Okay, if this is the case, then we say that there is a convergence. Okay, so here is a diagonal dominance, but it may not guarantee. Okay, so convergence is guaranteed, or convergence to be guaranteed. So here there is no guarantee. But if you have another matrix of this nature, 2, 1, 1, or say, let me write 1, 1, 4, 1, 1, 2, 3, x1, x2, x3 is equals to v1, v2, v3. Okay. Now here you see 2 is equals to 1 plus 1. 4 is greater than 1 plus 1. And 3 is equals to 1 plus 2. So all the conditions are satisfied along with this greater than condition. So this particular matrix guarantee, there is a guarantee. There is a confidence that is possible. It is highly possible. I mean, it is ensured that the convergence is achievable. Okay. So Scarborough Criteria says that AII should be such that they should be greater than or equal to the other sum of the other elements AII. Okay, where you say J now, JJ, where I should not be J should not be equals to I, and all other elements. So it should be okay. The coefficient AII should be greater than in each row and AII should be greater than sum of j is equals to 1 to n ajj at least in one row. If it is the condition is satisfied in all rows, that is fine, but at least one row should have the larger diagonal dominance. Diagonal element. These are all called as diagonal elements.
Excuse me, sir.
Diagonal elements.
Sir.
Diagonal entries or elements. Okay. So in one row, the coefficient AI in each and AI at least in one row should one row for the ensured convergence. Okay, this is a Scarborough criteria. Okay, Scarborough criteria. Okay, so you see that this diagonal dominance is must for convergence. Okay. Okay. Now, if we have this matrices, and suppose I want to again increase the diagonal dominance, of this term. What I can do? Suppose I want to increase only the diagonal dominance of this. So suppose I divide this by a large number, say 5. Then this value will become 0.4. So diagonal dominance gone by dividing it by a large number. There won't be a diagonal dominance. Suppose I divide it by a small number like 0.1. What will be value? 2 by 0.1 will be 20. Isn't it? Similarly, everywhere if I divide by the same number, you are going to get a large value. Isn't it? So 20 is greater than sum of 1 plus 1. 20 is greater than sum of 1 plus 1. 30 is greater than sum of 1 plus 2. So you see, by playing with the diagonal elements, you can actually increase the diagonal dominance of the matrix. Diagonal dominance can be increased. So I'll just write here. Diagonal dominance can be manipulated by operating it with, say, omega. Okay, say omega. And that is leading us to the method called as relaxation. Okay, so this lead us to relaxation method. Relaxation methods or relaxation method, you can say, which is called as successive relaxation. Okay, we'll be saying successive relaxation. Successive relaxation. Okay, now what do we do in successive relaxation? Essentially, we perform successive relaxation on Gauss-Seidel method, and according to Gauss-Seidel method, our general form can be written like this: x1 I is equals to 1, n is equals to 1, n plus 1, like that. That is a unknown 1 ai. A general formula can be written like this: di minus sum j is equals to 1, I is equals to I minus 1, aij xj n plus 1, isn't it? It is taking latest first value, and then, or maybe what are the values before just this, j is equals to I plus 1, sorry, j is equals to I plus 1 to rest of the values m aij xj and nth values. That is a general form for I running from 1 to m. This is a general formula. So we can write for this successive relaxation, we can write this x1 can be written as n plus 1 equals to x1 n plus 1 over a11 d1 minus a21 x2 n minus, say we are taking I1 to 3. Okay, so and also we are putting this residual, this term we are putting here, and this additional term we are adding. So d1 minus a11 x1n minus a12 x2n minus a13 x3n. Okay, x2n plus 1 will be equals to x2n plus 1 over a22 d2 minus a21 x1 n plus 1 minus a22 x2n minus a23 x3n. x3n plus 1 is equals to x3n plus 1 over 1 a33 d3 minus a31 x1 n plus 1 minus a32 x2 n plus 1 minus a33 x3 n. Okay. So if we reach to the exact solution, so this is the construct. Okay, here what we have done is this is a residual of this term. This xin is taken out and it is made like this. So what we are saying over here is this term will be as the exact solution approaches, xi n plus 1 values will be equals to xi n and these terms will be 0. Okay, so we make this arrangement and then now we say we'll use a successive relaxation method. Okay, so what we do in successive relaxation is we multiply this equation by omega. So here we substitute omega d. Okay, now we are talking about successive relaxation. Okay, so omega. At this omega has a range from 0 to 2 for convergence. Okay, and now if 0 omega 1 case is there, this is called as under relaxation. So omega is less means what does it mean? what will be, it is like omega divided by central coefficient. You also can say that central coefficient divided by omega. So central coefficient value will be, higher than, isn't it? If omega is small, between 0 to 1. So this is like making a diagonal dominance. So in general, we can write equation for this particular method is xi n plus 1 can be written as xi n plus omega aii di minus summation j running from 1 to I minus 1 aij xj n plus 1 minus summation j is equals to I m aij xj n, where I is running from 1 to n. So after some rearrangement, so same equation can be rearranged as omega aii di minus summation j is equals to 1 to I minus 1 aij xj n plus 1 minus summation j is equals to 1 I plus 1 m a ij Now here you see we have started with I plus 1 aij xj n bracket close plus this is there, and now I have taken 1 j is equals to I, so that we can say, and omega is there, so 1 minus omega, and ai will get cancelled out, so we can say xj n, xi. Okay, so if you see this is nothing but equals to xi n plus 1 is equals to omega times this, omega times this is nothing but the Gauss-Seidel. This is nothing but equals to Gauss-Seidel. This is nothing but equals to x I n Gauss-Seidel plus 1 minus omega xi n. Xi n is a correction. And omega is acting like a weight. for I is running from 1 to. Okay. So you see, in general, the relaxation method is like you multiply the Gauss-Seidel solutions, okay, by omega, and you add a correction here, which is 1 minus omega times xin. You calculate xin from Gauss-Seidel. You add this correction over here, and you get the new value. Okay. So rather than getting the value from the Gauss-Seidel, we add correction to it, and we get a new value. Okay. So what does it mean? Suppose Gauss-Seidel is taking this iteration, and this iteration, and this iteration. In one way, maybe we are doing just simply you are moving from this to this, skipping this iteration because we are adding to it. So this is not the exact value of next iteration is obtained. So you may add correction and you may get this new value, and you jump, then you add correction, you get now new value. So what do you see? This is a faster convergence. For some value of omega, it may not be a faster convergence. It may be from one to another, one to another, one to other, but that will be only in the case omega is equals to 1. Omega is equals to 1. If omega is not equals to 1, for omega is equals to 1, you get xi n plus 1 is nothing but equals to xi n Gauss-Seidel. Okay. For other values of omega, either you get this under relaxation situation or over relaxation. Now in under relaxation situation, we obtain omega running from the relaxation under relaxation, that is omega running from 0 to 1. Okay. So here any system which is non-convergent, which is non-convergent, convergent, can be made convergent, can be made convergent, can be made convergent. Also, it means that it removes oscillations present in the simulation, or present in the system. Okay. System may itself be having oscillations, and this can be. So what is doing, if you have a omega, small omega value, and you take A11, A12, A22, and A33, and if you divide it by omega, a small number, omega small number, omega small number, then A12, A13, and A23, so A21. So you see that again diagonal dominance increases, isn't it? So if the previous system where A11 was not diagonally dominant, by taking omega small, you can make that system diagonally dominant. Okay. So this is done by improving improving or increasing the diagonal dominance of the system. Okay. Now there is another case that we said that over relaxation. Over relaxation case is the one where you have omega running from 1 omega to 2. Omega value is from 0 to 2. 0 to 1 is under relaxation and 1 to 2 is the over relaxation. So now what is happening is that now we are dividing by the large number, maybe 2. So diagonal dominance is decreasing. Okay. So these methods are used for methods are used. I mean, this method with this relaxation. This method is used for system which are already convergent, diagonally dominant. Okay, otherwise it is not diagonally dominant. It should be first diagonally dominant. Otherwise, if the system is not diagonally dominant and you divide it by large number, again diagonal dominance is going to decrease. Now then, why do we need to divide it by this thing to decrease this diagonal dominance? Okay. So what may happen is that sometimes the system, now I say 2, 1, 1, 1, 2, 1 or 1, 1, 8. Now if you see here, this system, if you divide by 2, its diagonal dominance is going to decrease. But suppose there is another system. I am having this system 20, 20, 80, 1, 1, 1, 1, 1. Now if I divide this by 2, my next system will be 10, 1, 1, 1, 10, 1, 1, 1, 40. Now, still this system is diagonally dominant. But the diagonal elements are not very large. Now, if the diagonal elements are very large, if the diagonal coefficients are very large, then because you see here, if diagonal coefficients are very large means this next here this value will be, this total value will be very small. So if the diagonal terms are very large, then the convergence rate is very slow. Okay. Thus to accelerate convergent system over relaxation is used. Relaxation is used. Okay. And the methods we can say now successive over relaxation. Okay. It is successive over relaxation, like that. Over relaxation. Or we can say successive if our method is successive under relaxation, then you can say under relaxation, successive under relaxation. And since we are using Gauss-Seidel method, they are also called as Gauss-Seidel successive or relaxation, which is called as GSSOR. And here you can say Gauss-Seidel, GS under relaxation, GSUR. GSSUR, successive under relaxation. Okay. Now the question is, how to choose the value of omega? How to choose the value of omega? Value of omega in each case. In each case means, and for under relaxation, and over relaxation, or under and over relaxation. Okay. So the thing is, answer is trial and error. Trial and error. Okay. Because omega values are not, because omega values are not known a priori. They have to be, they are problem dependent. They are problem dependent. Problem dependent. Okay. So based on the problem, you have to see in that problem what omega value gives you acceleration or convergence. For convergence, you have to make under relaxation, and for acceleration, you have to use over relaxation. Okay. So and that omega for which you get acceleration and for which you get either convergence, those omegas are called as optimal omega. And that optimal omega optimal is problem dependent. Omega optimal in each case. This is problem dependent. Okay, that has to be obtained by trial and error. By trial and error. Okay, so I'll stop here, I think. Okay, thank you. Anybody is having any question?
Thank you, sir.
Any question? Anybody is having any question? Hello? Okay. Okay, so I'm stopping here. Huh? Okay, thank you.